I always love when we get to this slide in the course because it allows us to take a very simple equation that we started Biochem 1 with. Fuel plus oxygen gives us carbon dioxide, water, and energy, and really allow us to understand how that process works, how we take the three different macronutrients that we think about as fuels, carbohydrates, lipids, proteins, and how that ultimately translates to what we see with fuel metabolism. So let's start here in the center with our main fuel equation. Fuel plus oxygen gives us carbon dioxide, water, and energy. And so we're going to kind of map on all of the pieces that we know about this, but let's take a minute and first sort of think about what we know about the different fuels that we have. So let's think about the different fuels that we have. We know that we've got fatty acids, right? Those are going to be our lipids, fatty acids. We've got carbohydrates, and then we're going to have proteins. And so if we think about the different atoms that we have here that are present in these fuels, organic fuels, so they're carbon-based, so carbon and hydrogen, and then we consider oxygen and nitrogen. And why I've sort of written them in this way is we can sort of bracket and compartmentalize these, recognizing that fatty acids basically are going to be comprised largely of carbon and hydrogen. They are the most reduced fuel. That's why they're worth the most, why they're worth 9 calories per gram. Marching along here, we can see that when we have carbohydrates, and we use that sort of abbreviation for carbohydrates as a way to remind us that we have got carbon, hydrogen, and oxygen in our carbohydrates. More oxidized along that reduction oxidation continuum. Again, why carbohydrates are only worth 4 calories per gram versus versus lipids, which are 9 calories per gram. It has to do with where you are on that oxidation continuum. Proteins, again, have carbon, hydrogen, oxygen, but they also have that nitrogen atom. And that nitrogen atom is what sort of makes protein and amino acid metabolism a little bit unique, because when we break down those proteins to their component amino acids, we are going to have to split them apart essentially into the alpha keto acid group, right? And then we are going to have the nitrogen that we have to dispose of, and that nitrogen gets taken care of in the urea cycle. So we'll talk about in another video that's following here a little bit more about sort of how these different fuels are sort of broken down on a 30,000 sort of foot view here, and then where they're going to enter into this central sort of heart of metabolism. Remember, as we've studied metabolism here, we're very carbohydrate focused to start to learn these metabolic pathways, very glucocentric, very glucose focused. So we talked about glycolysis to take glucose into pyruvate dehydrogenase to convert it into acetyl-CoA. And that's an important branch point intermediate because any fuel can be made into acetyl-CoA. In our last learning unit, we took acetyl-CoA through the citric acid cycle, collected a lot of NADH and FADH2 along the way. And the key to this learning unit about electron transport and oxidative phosphorylation is to understand how we take those, energy harvesters as those B vitamins, NADH and FADH2, get those electrons to do the work of generating a proton gradient and using that proton gradient to synthesize ATP. So we're going to put all of those pieces that we just said in words there into play here in this chemical equation. Okay, so maybe the simplest piece is just to highlight that ultimately the carbon atoms that are in our fuel are going to become carbon dioxide. And to highlight the main places from a metabolic standpoint that we're going to see that happen is pyruvate dehydrogenase chemistry. And remember that that's exclusive to either glucogenic amino acid or glucose metabolism. But we're going to have the citric acid cycle. So remembering that any fuel can be made into acetyl-CoA, taking that acetyl-CoA through the citric acid cycle, that's where the bulk of carbon dioxide for fuel metabolism is generated. And so we're going to have that then generate that CO2. So that sort of connection is pretty straightforward. We're going to go through the rest of this sort of connection here to understand how fuel metabolism, fuel oxidation, is ultimately going to generate the water that we see in this chemical equation, and importantly, the ATP that we have. So remembering, fuel when we're metabolizing fuel, it's really oxidation. So when we metabolize fuel, That's really oxidation. So oxidation is the loss of electrons, okay? Remembering that electrons are bonds and bonds are energy, right? So that's why our fuel is worth something, because all of those atoms are connected together with bonds. Bonds are electrons. Electrons are energy. So when we break that fuel apart, we want to harvest that energy as electrons by storing those electrons in those reduced cofactors. So those electrons are going to go to NAD plus and FAD. These are the oxidized forms of those B vitamins, remembering that NAD plus is going to be vitamin B3, FAD is going to be vitamin B2, so just remembering our B vitamins there. When they take on those electrons, they're going to adopt their reduced forms. So NADH and then FADH2, so these are the reduced forms. And this is the way, again, of collecting and saving the energy of fuels as reduced coenzymes. I really should use the word coenzyme because we're referring to those B vitamins, okay? Now, ultimately, those guys are going to lose their electrons when they give them to the electron transport chain. So we're going to get to those in a minute, but when they lose those electrons, these guys return to their oxidized state and can go back and pick up more electrons from fuel oxidation. Okay, so when we talk about the loss of these electrons, they're really taking those electrons and going to the electron transport chain. So the electron transport chain, we're going to learn the details of this. That, again, is going to be the focus of this learning unit. The electron transport chain takes those electrons in, allows them to go through a series of complexes that ultimately are going to generate a proton gradient. So generate a proton gradient. Okay, so this process we're going to be referring to as ET for electron transport, and then that oxidative phosphorylation process uses that proton gradient to synthesize ATP. So we're going to synthesize ATP, remembering that ATP is what our biological money is, right? So ATP is our biological money. So this is oxidative phosphorylation. Okay, so this is oxidative phosphorylation. This is going to be the OP part. All right, we got one more arrow to kind of fit in here, and that's understanding how we generate water. So going to have a little overlap here as we kind of like have an arrow that's got to go under some stuff that we have here. After those electrons have gone through the electron transport chain, generated their proton gradient, we're going to learn in this learning unit how that happens. That proton gradient gets dissipated. So the electrons then, once they exit the electron transport chain, I actually should show them going this way. We're going to take those electrons from the electron transport chain. They're going to kind of come over here. They're going to get delivered to oxygen. Okay, and then that's how we generate water. So again, the reduction of molecular oxygen is how we are going to generate water. So here is our oxidation piece, right? We're going to be generating CO2, but that is, again, the fuel that has lost their electrons, go through the electron transport chain, and the end of the electron transport chain is ultimately taking them and then delivering them to molecular oxygen, reducing that molecular oxygen to water, and we've generated all the pieces that we have for our main fuel equation.